All right, so 1.3, evaluating limits analytically, fancy word for algebraically. So the first thing we should do is direct substitute every single time. And so if I have this limit as x approaches c of our function, we just try to direct substitute. And if it's well behaved, like Emil, it'll work out and nothing will need to go on further. All right, and so that's what we try to do first every single time. Be it a constant or a polynomial of sorts, we try to substitute in to see if it works. So let's look at part A. I have a limit as x approaches 2 of 3. Do I have anywhere to substitute in on this one? No. So guess what it still is? 3. So my limit is 3 the whole time. It's constant. All right, the next one, the limit as x approaches negative 4 of x. So guess what I replace x with? Negative 4. So my limit is negative 4. Oh man, I got to think a little bit on this one, not a lot of bit. But if I have a limit as x approaches 2 of x squared, what do we substitute in? 2. I bet Mr. McKnight could even do this one. What do we get?
2.
2 squared, which is? 4. Here we go. So all of your mathematics beforehand will still apply with limits. All right. So sometimes you'll have a scalar multiple. You can bring out that coefficient basically out front, and then work with your limit statements. Addition, multiplication, division. They all work with limits, just like you have before. All right. So here we go. Again, we try to direct substitute every single time to see if it works first. So I have a limit as x approaches 2 of the quantity 4x squared plus 3. So what do we try to substitute in? 2. And so now I substitute in. So Ethan, when we substitute in 2, what do we get? 2 squared, which is? 4 times 4? 16. Plus 3. So we end up getting this limit is equal to 19. All right, this next one. I have a limit as x approaches 1 of the quantity x squared plus x plus 2 over the quantity x plus 1. So again, we try to direct substitute, Mr. Nance. And so now, what do I get in my numerator? 4. What do I get in my denominator? 2. Could we simplify that? Yes, sir. So it goes to what? 2. So now we have a limit equaling 2. All right, let's look at this one. So again, we try to direct substitute, even with it's a trig function, so we need to know our unit circle again. It's going to come up frequently in this class. All right, and so let's look at number 1. So I have a limit as x approaches 0 of tangent x. So I substitute in 0. So what is the tangent of 0? 0 over 1, which is 0. Exactly. All right, let's look at number 2. So now I have a limit as x approaches pi of x cosine x. So I replace the x, I direct substitute x in, I direct substitute pi in for x. So now I have pi times cosine of pi. Well, what is the evaluation of cosine of pi? Negative 1, because it moved left. And so now I have pi times negative 1, which we can simplify to negative pi. This next one, I've changed it a little bit. I'm going to do a limit as x approaches pi over 4 of sine squared x. The one thing I want to get with this is a composite, all right? And so what is your outermost composite? What is the outer part of this function? There's a sine function and then there's a squared function. Which one's the outer composite? The squared part is the outer. And so I have to do that second. And so my inner composite is what? The sine. And so that's what I have to evaluate first. Remember how we have to go inside out? Yeah. All right, and so that's what I wanted to hit here. And so what is the sine of pi over 4? Square root 2 over 2. And so now we'd end up having square root 2 over 2. And then I want to do what to it? I want to square it. And so square root 2 squared is 2. 4. 2 squared is 4. So then I'd end up with what, David? 1/2. So before I move on, I want to do some algebraic review. So back in Algebra 2, you did a sum and difference of cubes. Now, I honestly don't use sum and difference of cubes that often. And later on this year, we'll meet a guy named Guillaume L'Hôpital, and I won't have to do this anymore. All right? But until we know calculus, I can't actually do this any other way. And so we have to use our algebra skills, which we're all very, very good at. And so I have a cubed minus b cubed. Does anybody remember what it factors to? It actually factors to a minus b, that quantity, times a squared, and then plus ab plus b squared. All right? And then if you have a cubed plus b cubed, that's a sum of cubes. That actually factors to a plus b times a squared minus ab plus b squared. All right, so if you were trying to memorize it, if you have a minus, you start out with a minus, but then this one is a plus. And then if you start out with a plus, this one's a plus, but then it goes to a minus in that part. That's the way I kind of think of it in my head. All right. All right, Lucas is going to read this part for us. Here we go.
Let C be a real number and let f of x equal g of x for all x is not equal c in an open interval containing c. If the limit of g of x as x approaches c exists, the limit of f of x also exists, and the limit of f of x as x approaches c equals the limit of g of x as x approaches c.
All right, fantastic. And so this is a strategy if we get an indeterminate form. I want you to write out indeterminate form, and then I want you to write out 0 over 0. We've dealt with 0 over 0, and this is actually the indeterminate form that we're mostly going to use, pretty much like 98% of the time in Calc AB. All right? In BC, I get to talk for a couple days on different indeterminate forms, but this is our guy this year. All right? 0 over 0 is our indeterminate form this year. All right? So what is 0 over 0? We know this, though. It's a hole. And so does a limit exist at a hole? Sometimes. Sometimes. That's the one I want to know. All right? But it could exist at a hole, right? And so that's where we have to go into like further exploration on it. And so before we did things like with a graph or numerically, now we're going to do things analytically. So we have to use our algebra skills today. So let's look at this one. So now I have a limit as x approaches 1 of x cubed minus 1 over x minus 1. And so if I substitute in 1, what happens? I get 0 over 0. So I got this indeterminate form. It's going to be a hole. So what do I need to do? I need to keep going. And so we just practiced our algebra review on factoring. And so what does x cubed minus 1 factor to? X minus 1, and then x squared plus x, and then plus 1. And then it's all over what? X minus 1. And so now I have this limit. Now, what cancels? X minus 1s cancel. Is that a shocker to us? No, because what was it going to create? A hole. And so now I end up having this limit as x approaches 1 of the quantity x squared plus x plus 1. Now when I direct substitute, what do I get? I get 3. And so now this limit as x approaches 1 is equal to 3. This is actually a huge concept in our limits, in our calculus, basically. All right? So this function right here, I'm going to use this little cursor. This function, this x cubed minus 1 over x minus 1, is the same as this function except for at its hole. Do you see how it's like the same function except for at this hole? All right, and so we had to simplify or manipulate to get this simpler function to evaluate it to find out where the hole is. All right, so let's look at this one. So now I have x, limit as x approaches negative 3 of the quantity x squared plus x minus 6 over x plus 3. And again, what do I try to do first every single time? Direct substitute. All right, so when I substitute this in, I get negative 3 quantity squared, which is 9. 9 minus 3 minus 6 is a what? 0. So I get 0 up top. What do I get in the bottom? 0. Oh, crap, something happened. So what should I do? It's an indeterminate form. So what did it create? A hole. It created a hole of 0 over 0. So what do we like to do to quadratics? We like to F them up. All right. And so what does it factor to?
AC method, negative 6, so then you do x minus 2 and
X minus 2, and then x plus 3's. So what happens to the x plus 3's? They cancel out. How convenient. And so now I have a simpler function. This is where I need to see good notation. I have a limit as x approaches negative 3 of the quantity x minus 2. All right? That's what I need to see right here. I'm honestly not going to grade the blue part, but I'm going to grade the red part. All right? And so now I substitute in negative 3, and so where would I have it at? Negative 5. And so what really happened is what I had a hole at negative 3 comma negative 5. That's really what's happening graphically. All right? Pretty good? All right, we are moving. So strategies right now is factor. Okay? If it gives you an indeterminate form, we factor. But what do we need to do first every single time?
Try to
Direct substitute. Okay? And if that works, it's well behaved, it's beautiful. All right? It's all good. However, if it gives you an indeterminate form, what's our one thing that we have to do right now? Factor. All right? And then you can use a graph or a table to kind of reinforce it, but really, that's what we're going to do analytically. All right, and so there's your homework, page 67, numbers 17 through 25, all, and 30 through 54 even. Who is that?
Wait, what's the page again? I think that's full times X.
Who is that? Right, so again, this is our second part of 1.3. What do we try to do every single time? First, we try to do what? Direct substitution. So if I have this limit as x approaches 0 of square root of x plus 1 minus 1 over x, what happens when we substitute in? We get 0 over 0. So right now, our only technique is to factor. Can we factor this?
Nope.
No. All right. So what do? We multiply by its what? Conjugate. All right. So we need to multiply by its conjugate. So what is its conjugate? Square root of x plus 1 and then plus 1 over the square root of x plus 1 plus 1. And so now, because we multiply by the conjugate, it's just like the Florida part, the F and the L of the FOIL. All right, so the first part multiplies to give me what?
Square root of x plus 1 squared.
Okay, so that is just x plus 1. And then the last part, so negative 1 times 1, which is what? Negative 1 over x times the quantity square root x plus 1 plus 1. And so now lovely things are about to happen. All right, and we have to go in order of these things. So what cancels in my numerator?
The negative 1, positive 1.
The ones cancel. Now what's allowed to cancel?
The x.
The x's are allowed to cancel. And it has to go in that order. All right. And so now I end up having my simpler function. I have a limit as x approaches 0 of who's in my numerator now? It's a placeholder. 1. All right. And then I end up having the square root of x plus 1 plus 1. All right. And so now I'm ready to direct substitute. This is my simpler function. This is where I need you to get to. I'm honestly not going to look at this part too much. This is where I'm going to look. And so now I substitute in 0. And so what do I get? I get 1 over 2. I get 1/2. All right. And so that created a hole at 1/2. All right. And so that's how we need to do it analytically or algebraically. However, I'm going to show you right here that it's proven with a graph and a table. So again, what's a limit when you go from what? Both sides arbitrarily close to a what? A y value. And so when I go from both sides, I go from the left and I go from the right, where does that hole look like it's supposed to be? At 1/2. And then we worked with the table. Again, where does it look like it's supposed to be? At 1/2. However, we're going to mostly do things analytically because we won't have our graphing capabilities or our calculator capabilities on most of our stuff. All right, we're moving. So this is called a squeeze theorem. I am briefly going to talk about the squeeze theorem. All right, it's sometimes called the sandwich theorem or the pinching theorem. And this is what it is. You basically know what's on top and what's on the bottom, and then you figure out what's happening in the middle. These are the two special trig limits that I need you to write down. All right, these are the two. So the first one we visited a few days ago. the limit as x approaches 0 of sine x over x is equal to 1. And I proved it with a graph, and I proved it with a table. I cannot prove it too much analytically yet, even though I'm going to use the squeeze theorem today to prove it. All right, and then this is the other one that I need you to write down. The limit as x approaches 0 of 1 minus cosine x over x is equal to 0. I am briefly going to prove to you sine x over x is the limit as x approaches 0. All right, and so we're going to use the squeeze theorem real quick. So can everybody agree that the major triangle over here on my unit circle is larger than the area of the sector? And then if I take away the little slice of the pizza and I make another triangle inside, that triangle is smaller than the sector. Cool. And so because we know trig, the area of that triangle is tangent of theta over 2, and this is theta over 2, and this is sine of theta over 2. Okay? All right, and then everybody in their right mind would multiply everything by 2 over sine theta, obviously. All right, that would be our next step. Just makes sense. Just kidding. Nobody would do that, but this one right here. All right, so then I end up getting 1 over cosine theta is greater than or equal to sine theta, or theta over sine theta, which is greater than or equal to 1. And then, obviously, you take reciprocals and reverse the inequalities, and so then you're left with this. You're left with cosine theta is less than or equal to sine theta over theta. That's the one we're working with, which is less than or equal to 1. Well, what is the cosine of 0? So if I did a limit as x approaches 0, or theta approaches 0, I should say, what is cosine of 0? 1. And so I have 1 on this bound, and I have 1 on that bound, and so my limit as theta approaches 0 of sine theta over theta is equal to what? 1. And that's how the squeeze theorem actually works, but it will not be this crazy when we start doing things. Okay? So we're going to utilize that, though. So I have this next one. I have the limit as x approaches 0 of tangent x over x. What do we try to do first every single time? Substitute in. So what's the tangent of 0? 0. 0 over 1. And then I put it over 0, so I get an indeterminate form. I get a whole, don't I? And so we have to manipulate it. And so we know two things right now. We can factor or we can rationalize. Do either one of them work? No. So I got to use something else that I know. And so it's going to be one of those two things that we just wrote down. What do we think of tangent as? Sine over cosine. So that's what we're going to manipulate it as. So I'm going to say the limit as x approaches 0 of sine x over cosine x. And then dividing by x is really just like multiplying by 1 over x. All right? However, I kind of want to group new things together. And so what needs to kind of go together for something that I know? The limit as x approaches 0 of what? Sine x over x. So I'm going to manipulate it so I can put those together. Of course it is. All right, we're just manipulating here. All right, and so now, what is my limit as sine x over x as x approaches 0? What does this part go to? 1. That part goes to 1. And so this part goes to 1. And then I substitute in 0 for cosine. And so what is cosine of 0? 1. And so now I have 1 over 1, which is 1. And so guess what my limit is? 1. All right, so now we have a limit as x approaches 0 of sine of 4x over 3x. So I want to kind of go off to the side for just a sec. I want to call the limit as x approaches 0 of sine of 2x over 2x. That is actually the same as sine x over x. All right? Is everybody following me? So it's a 2x over 2x, which is good. And so that's equal to 1. So right here, I have a sine of 4x. First of all, can you factor out the 4 from the sine trig function? No. Okay, that's breaking math rules. You will kill kittens. We don't want to do that. All right, and so then, what do I want on the bottom then? 4x. I want a 4x on the bottom. Well, there's a 3x right now, so I need to put a what? I need to put a 4 on the bottom, don't I? But if I put a 4 on the bottom, math's an equal opportunity sport, so what do I need to do?
Put a 3 on top.
I need to put a what?
3 on top.
Not a 3, a 4. Okay. All right. If I put a 4 on the bottom, I got to put a 4 on top. All right. Okay. So now I end up having my limit as x approaches 0 of sine of 4x. I got a 4 chilling out front still. But what do I want to put this sine of 4x with? Not a 3x, but a what? A 4x. And what's going to be on the outside? A 3. Now, I hear some people saying, I want a 12x. Yes, 3 times 4 is 12. But that's not the way I want to look at it. I want to look at it as sine of 4x over 4x. Because what do I know that this part's going to go to? That part's going to go to 1. Bless you. And so now I end up having 4/3 times 1, which is 4/3. And so then that is equal to 4/3. Now, I will have a decent amount of people on my quiz and tests get 4/3 as an answer. However, I will still take a point off because they got to it the wrong way. I'm going to show you a naughty way to do it. So this way, if you have like a sine of 4x, guess what people do? They like factor out the 4. And they're like 4 sine of x over 3x. Now, will you still get 4/3 as your answer? Yes. However, did you take the right road to get to the answer? No. Okay. There are many ways to Tampa. However, you got trapped and you just got lucky. All right. So this is breaking math rules. I will not actually give you full credit for that. All right. So that is naughty. No, no, no. All right, so this is one from our homework set that we're going to do. So now I have a limit as x approaches 0 of 1 over the quantity 3 plus x. I prefer x plus 3 for some reason. I just use my commutative property. And then minus 1/3 over x. So again, what do we try to do first every single time? Substitute in. Guess what happened? You got a hole. All right, and so now we have to use some algebra skills. And so now the first thing we need to do is we need to distribute dividing. And so now I'd end up having my limit as x approaches 0 of 1 over x times x plus 3 minus 1 over 3x. So that was our first step. And so now instead of a fraction, or what we call a complex fraction, now I just have 2 fractions. And how do we add or subtract fractions? What do we have to have? We need common denominators. So what does the left one need? What does this one need then? It already has an x. So it just needs a what? A 3. So I'm going to multiply this one by 3 over 3. And then what does the right one need?
We know that you have
I need an x plus 3. So I need to multiply this one by x plus 3 over x plus 3. And so that gives me my denominator of 3x times x plus 3. So now we just need to figure out what's happening with my numerator. So I end up having 3 times 1. What is 3 times 1?
3.
3. And then I end up having minus 1 times the quantity x plus 3. So now I have the quantity of x plus 3. What would I highly suggest you do with that subtracting a quantity thing? Distribute the negative. So now we're going to go boom, boom, boom. All right. And so then what cancels out? The 3's in my numerator cancel out. So these 3's cancel out. Then what cancels out? The x's cancel out now. So those 2 x's cancel out. And so now I'm ready for my simpler function. So now I end up having my limit as x approaches 0 of what? Who's in my numerator now? Not negative x, but negative 1 over 3 times x plus 3. And so this is where I'm looking. That's my simpler function. And so now we substitute in 0. And so when I substitute in 0, what do we get? Negative 1/9. All right. And so my limit of my original is also negative 1/9. All right. This next one, I have a limit as x approaches 4 of the square root x plus 5 minus 3 over x minus 4. So what do we try to do first every single time? Substitute in. What happened? 0, 0. So what do I need to do?
Rationalize.
We need to rationalize. All right. And so what do I multiply by?
Square root of x.
Square root of x plus 5. And then what?
Plus 3.
Plus 3 over the square root of x plus 5 plus 3. And so again, the FOIL part, I just need the Florida on the numerator. And so now what do I get? X plus 5 and then minus 9. Beautiful. And then on the bottom, I end up having x minus 4 times the quantity, square root of x plus 5 plus 3. Right? All right, so what happens, Yumil? And then?
And then
You're welcome.
I get it.
So what happens? What do we got? What do we get in the numerator? X minus 4 in our numerator. So we get x minus 4 in my numerator. What does that do?
It makes a whole.
It cancels out the x minus 4. So that numerator and x minus 4. So something convenient happened again. Okay? And so now I'm left with my simpler function. So now I have a limit as x approaches 4 of 1 over the square root of x plus 5 plus 3. So now what do we get to do?
Direct substitute.
We get to substitute in. And so when we substitute in, what do we get? We get 1/6. And so my limit is equal to 1/6. Just a little bit more homework. Page 68 this time. Numbers 55 through 62, 65 through 73, 85, and 86. All right. That's Jamil when he gets older. All right.